Hello, good morning to everybody. It gives me great pleasure to introduce the first speaker in this session, Professor Riddhi Shah. Professor Riddhi Shah is from Jawaharlal Nehru University, Delhi. She did her master's at IIT Bombay, and she did PhD in the Tata Institute of Fundamental Research. She was a recipient of the JSPS, and that is from Japan, and the Humboldt Fellowship from Germany. She was honored with the Young Scientist Award by DSD, and she was one of the contributors to the book which you have been hearing for the past 2 days, Leelavati's Daughter. She was at TFR for many years and is now Professor of Mathematics at Jawaharlal Nehru University at Delhi. Her areas of research are Lie groups, probability, ergodic theory, and dynamical systems. Today she will speak on dynamics of distal group actions. Professor Shah.
I would like to start by thanking the organizers, Vaijanti and Jaya, who has given me this opportunity by inviting here. And I am from, as you all know, Jawaharlal Nehru University. That stands for School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Let me tell you just two-line introduction. We are a new department, new meaning 4.5 years old, and we have 100% women faculty there. Namely, we are 2 women faculty, but we have advertised and we'll soon have more people, and we offer a PhD program in pure mathematics, and once we have enough strength, we'll start with MSc, and so all of you are welcome as students and faculty in our School of Physical Sciences. And as I mentioned yesterday, the women students get 5 points extra in their entrance exam result. Plus, if you are from a backward region, as they put it, means rural areas, they have they give 5 points for that also. So this is to bring women and people from rural area at par with people from urban areas and men, just to give them an opportunity, and it's not too much points, so you would still not feel too bad about it. So please think of JNU. And I would like to, at the outset, apologize to so many senior people because my talk is really elementary. If they want more detail, they can contact me later. I've just made it very simple by taking just one case and working on it. So and anybody has any question or difficulty following, please stop me. And let me start. So I'll start by dynamical systems. So what are dynamical systems as such in real life? It's study of behavior of anything that moves with time. Roughly speaking, that is what it is. People who do applied maths know this better. So flapping of butterfly wing, it could be as gentle as that, or it could be as violent as water wave, tsunami, tornado, or it could be something like motion of a particle, or oscillating chemical reactions, as you will see later. It could be growth pattern in cell or even animals or human being. Growth pattern trajectories with time. And it could also be neuronal activity. There is a large group of people working in neuron activities in US. For example, New Jersey Institute of Technology has a huge department. We had a visitor from there, and this is a applied dynamical system. They are all applied mathematicians. And the dynamical system could be discrete in time or continuous in time. For example, you want to study, say, shares and stock every day at, say, 11:30 in the morning. Every day you want to see what it is. Then it's a discrete time because today, tomorrow, day after, you can see and study the behavior. Or it could be continuous with time. For example, moving pendulum, single or double pendulum, or continuous cell division or growth patterns, or these oscillating chemical reaction. Let me show some specific examples now. So as you can see, single pendulum behaves nicely. It has a regular behavior, and unless there are external forces involved, it will just continue doing what it's doing by oscillating from one. It has the same trajectory. While if you have a double pendulum, this is called a double pendulum. So there is this one axis fixed and, sorry, and the other, so there are two of these pendulums attached to each other, and if you study the trajectory of this point moving in the space around it, it moves in a bounded compact space, and this is how it looks. In fact, as t goes to infinity, it just fills up, it becomes dense in this compact part, and it's a chaotic behavior, not regular like single pendulum. And so in mathematics, chaotic in some sense defines ergodicity, because it fills up the space. And so ergodic, you want to study a chaotic behavior, you have to have an ergodic model. So this is chemical reaction. This is called Belousov-Zhabotinsky reaction, and this describes changes in chemical reaction. One side is the actual chemical reaction, and the other side is given by the diffusion equation. This is a model which is pretty close to that. Of course, for a layman it doesn't look very close, but it does describe these reactions. And this one, for example, I was mentioning, we had a colleague, Amitabh Bose. He works in this neuronal activity of brain. He's an applied mathematician, and the goal is to study and model how neuron behaves in brain. And in fact, they help biologists by providing model and for studying this behavior. And Hodgkin and Huxley derived this equation in 1950 to describe this, and they found that neurons behave almost like electrical circuits. So as you see on the top, it is example of a trace from a bursting neuron related to breathing. So when you breathe, it moves like expanding and contracting in some sense. And these lower two figures are actually using differential equation, and these are the models which you get from that. Okay, so now I have given you some examples, but as you all know, I am a pure mathematician, or at least let me tell you, I am a pure mathematician, and I work in pure mathematics. So how would you view dynamical systems in mathematics without all the examples? How would you view dynamical systems? So roughly speaking, you say X is a topological space and T is a continuous map from X to X, or it could also be from X to Y, but basically you take X to X, and it is we say that Xt is a dynamical system where X is a topological space and T is a continuous map. What is a topological space? You can take it as plane space R2, Rn, or you can take unit circle, or you can take matrices with usual metric topology. You can, so topological space you can take it as just metric space if you like, or you could also take discrete space, finite groups, group of integers, and so on. Or a compact bounded region in a plane, like say pendulum, say double pendulum had that trajectory which, if you take a closure of that space, it is a bounded region. So you can take bounded compact space for x, and T is a continuous map. So x could be compact, bounded, or non-compact, unbounded, and T could be ergodic, chaotic, or regular. In sense, for example, double pendulum gives you ergodic behavior and single pendulum gives you regular behavior. And T could represent discrete or continuous time, as I said. So if you are tracking something continuously, that is continuous time, which would be parameterized by T sub T, as we will see later. And if it is one particular fixed discrete time, then it would be just that discrete T. So you will take T, then apply T again, you get T squared, T cube, and so on. So in case the map is ergodic, there is one orbit of T which is dense in x, like in the path of double pendulum. But if it is not ergodic, it could be dense or not dense. So in ergodic case, T to the power nx is dense in the space, or Tx is dense in x. And it's not very sensitive to where you start. Pendulum, you just let it go, and it doesn't matter what force you give, how much, and it would still fill up the space. So space is topological space. So here in case of pendulum, you have a compact, just the compact region, depending on how big the pendulum is. So I'm going to talk about finally actions on groups. So it will be a topological group, or you can take it as vector space and homomorphisms acting on. Is there a problem? So what are distal maps? So distal map, so a map from topological space x to x is said to be distal if you take two distinct orbits. Orbits are just, you take a point, and if T is the map, T to the power nx, that is the orbit of it. It stays away, so if you take two distinct points, x and y, T to the power n x and T to the power n y, stays away at some. So if you are stay away from each other, in the sense that if you are in a metric space, then there is some minimum positive distance between T to the power nx and T to the power ny, no matter what the n is. So basically, if you are in x cross x, then T to the power nx and T to the power ny does not go close to the diagonal. That's what. As n tends to infinity, it remains away from the diagonal. So distal maps were introduced by David Hilbert and studied by many mathematicians, Furstenberg, Abel, Oslander, and Rani, and others. So why do we study distal maps? I gave you some example of dynamical systems, but in mathematics also it has applications. So distal maps are important for many reasons. It facilitates the study of non-ergodic maps. Also, if you take a group, for example, like R or Z, or general linear group GL and R, and you take unipotent groups, whatever you like, or compact groups S1, then there is a concept called distal groups. Namely, in distal group, the conjugacy action is distal. Means if, for example, pointwise distal group, if I take any point and I take its conjugation action, take x going to g x g inverse. So next time it is x going to g x g inverse, g square x g inverse, g cube x g inverse, g to the power minus 3, sorry. And that action should be distal. Means if I take 2 points, this conjugacy class of these 2 points should in some sense remain parallel or at least little apart. So abelian groups, finite groups, because they are compact, and nilpotent groups, all these are distal groups. Okay. So on these distal groups, you can characterize behavior of probability measure. As you take powers of probability measures, they sort of flatten out. So when you in other class of groups, the behavior of probability measure, as you take power, it becomes like concentrated on small compact sets. It just keeps getting a peak there, while here, for example, on Rn, you take Rn is abelian, so it's distal, and you take probability measure and then take its power. It just keeps flattening out when you convolution power, sorry, yeah. So you take convolution. So I'm not going too much in detail because many people may not know convolution. So, so in fact, these are characterized by this. This result was done jointly with C.R.E. Raja from ISI Bangalore, that there is a 1:1 correspondence between the behavior of all measures on a group and the distality of the group. And this is for locally compact groups. And here we are going to talk about when you have these distal actions, the space splits into ergodic component, means there are minimal closed invariant T invariant sets, say, and on each of it the orbit of any element is dense. So these are called topologically ergodic components, as we will see later. So I will just start by some examples. So if you take a real line R or Rn and you take Tx equal to, Tx equal to, actually this is R into x, not R. So R is a real number, okay, positive or negative, and it is just Tx equal to R into x. Those of you who know group structure, this is a homomorphism, right? And if R is not 0, it is 1:1 onto bijection from R to R. And it's distal if and only if R is plus or minus 1, because if you take, in this case, t to the power nx is x or minus x, and if I take two different x and y, they will just remain at that distance x minus y, because they are distinct. Now if you have R is less than 1, then t contracts any point and any orbit goes to 0. Means if I take, say, t to the power 1 x, it is r to the power n x, and since mod r is less than 1, this quantity goes to 0, as it's simple, right? It's just you're multiplying. Suppose r is half, then half, 1/4, 1/8, 1/16, it will just go to 0 no matter what the x is, right? But on the other hand, t to the power 0 is, t to the power n of 0 is always 0, right? So you cannot separate out orbit of 0 from orbit of x, right? That is why these are not distal. Now the same thing is true for Rn, but if you take any linear transformation of Rn, like T is in GL and R, so maybe I would like to write down something. So if you take x equal to Rn, and T is a linear transformation, so everybody knows that it can be given by a matrix. So T is in GL and R. So this is a matrix acting on Rn, yeah, and I am taking non-singular because I want that it is a bijection, and if it is not 1:1, anyway it's not distal, so it's 1:1 and hence on to, and T is distal if and only if the eigenvalues of T, because it's a matrix, right, eigenvalue of T are of absolute value 1. So the moment it has eigenvalue which is of absolute value less than 1 or greater than 1, there would be some x such that t to the power nx will go to 0 in Rn. And the same thing is true for, if you know Lie groups, then this should be true on the induced map on the Lie algebra. Yeah, because then the negative orbit will go to 0.
So R can be any whole number?
Yeah, R can be any whole number also, but not 1. If it is 1, then it's distal. If it is 2, then it's not distal, because 2 inverse is half. So T inverse of X would go to 0. So let me put this, that on R is distal if only if T is distal. So Tx is Rx is distal if and only if R is plus or minus 1. So if R is 2, then R inverse is half. So T inverse X is half X, and then T to the power minus X minus nx would go to 0. Okay, so it's a group action, the group generated by T. In fact, it is more general than one thing. You can take a subgroup of GL and R acting on Rn, and you take its action. That is how it's done, but I'm not going to talk about that. So most things are done like that, but I'm concentrating on one because it's easier to study and understand one of them. So if you have a Lie group, then same thing should, so an automorphism, which is a bijection continuous homomorphism, and its inverse is also continuous, that is an automorphism of a topological group. So if you take G a Lie group, then T is an automorphism which is distal if and only if dt, which is induced on the Lie algebra, should have eigenvalue or absolute value. So now that was on non-compact space, Euclidean space. Now let's see what happens on circle or torus. So this is rotation on unit circle. Everybody knows rotation on unit circle, I suppose. So if you have a map T from S1 to S1, is a rotation. Tx is Rx, where R is e to the power 2 pi I theta for some angle theta. Now if theta is rational, in the sense it is, say, some A by B, where A and B is non-negative and A is B is not 0, then if theta is a rational angle, you know that when you take Rx, R square, Tx, T square x and so on, it would be a finite orbit, because some power would become an integer, and then integer power, and then it would come back to itself. So if theta is rational, then it is a finite or periodic orbit for any point x, because it just shifted. And if you are shifting, like say pi by 2, then pi by 2 pi, and when you take 2 pi again, you will be back to the same point. And if theta is irrational, then any point has a dense orbit, and in this case the map T is ergodic. But in both these cases the map T is distal, because when you take 2 points, every time it is moved by a fixed angle, so the distance remains same between those 2 points. They will never, the distance will not reduce and they will not merge. So let me show you an example. So there is a pictorial description. I am very bad at drawing pictures or doing anything, and my former colleague Amitabh Bose had made this. You can see. So this will show periodic orbit. So you see there is an angle which is roughly 45, you can say. Okay, he's done it by hand, so don't look too closely, otherwise you will be disillusioned. So this is a periodic orbit, okay, 90 degree, and this one is slightly close to 90, but maybe 80, between 85 and 86. So this is a dense orbit. So the element I started there, and it will keep moving. This is the second cycle it has crossed. It will never go back to that point. It can converge to that point, but it will never go back to this point. So this is the second cycle, and third and fourth cycle you can see. So you can imagine that this is fourth cycle. If I keep on doing, it would sort of densely fill up the space. Yeah, it won't be all the points, but it would become a dense subset. Okay. So, so that was one example. Similar thing you can do for powers of S1 or so now I'm going to talk about orbits of T. Yesterday this Preena also talked about orbits of maps, right? And for compact space you can also take projective space CPN, which Usha talked about, and take a general linear group action on it, or take any linear map, and that would keep. So take a map in GLNC and you take CPN, it also acts on CPN. So you can discuss that, and behavior would be similar like on RF. So a map is said to have MOC, means minimal orbit closure, if the closed orbits are minimal closed T invariant sets. Means what? See, they are T invariant when I take orbits, right? Because it's just taking closure of a T invariant set, T to the power nx, n belongs to z, means positive and negative, so it's T invariant, and when I take closure of that set, it is naturally T invariant. But what it says is it's minimal, means if I take any other point in that orbit closure, and if I take its orbit, that would be same as the whole orbit. So if I took y in closure of T n x, and if I took T to the power n y and took its closure, that would also be same as this, closure of T n x, okay. So there is no proper subset which is T invariant in these orbits, okay. So MOC stands for minimal orbit closure. Minimality is because that's the smallest closed minimal T invariant set, and naturally if T has MOC, then T x, the space, if I take different orbit, they are distinct and they are minimal. So the each element would give distinct minimal invariant orbits, and the space X will split into this union of closed sets, okay. Because, and on each component they are T invariant components, means each orbit basically closed orbit closures are T invariant. So I have a T action on those subsets, closed subsets, and or you can say subspace, closed subspace, and the T action on each of the component is ergodic, topologically ergodic, means that any point would have a dense orbit on in these components. So let me give you one simple example. I'm going to talk about torus. So if you take a torus S1 cross S1, it looks like a donut. I'll just show you in a minute. And I'm taking this unipotent action, which is TRS is RS into S. So second component remains as it is, and the first component is rotated by the second component. That is what it means, okay. So I will show you in a picture in a minute. So this map is distal because you can check, you take, so in a group a map is distal if and only if its orbit doesn't converge to, orbit closure doesn't have identity in it. That is the equivalent condition. Because it's a group with identity and these are homomorphism. So homomorphism is a distal map if and only if its orbit closure does not have identity. Means if I take any non-identity element, then T to the power n k x should not converge to identity. That is what it means. So you can easily check with this map that if it converges to identity, both R and S would be identity, because T square x is RS square S, T cube x is RS to the power n x S, and so on. So the second component has to be identity if it converges to identity, and then obviously the first component has to be identity. And here orbit is either finite periodic. If S is a rational point, then it is finite periodic orbit, and or it is dense in a circle of the form S1 cross S. As I said, second component is kept invariant. So it is orbital is dense in this, or it is a finite periodic orbit. So no orbit is dense in torus S1 cross S. So it's not an ergodic map to start with, but it splits into ergodic component. So this map also has MOC, and we show some pictures here. So for example, this is a torus, and if you cut it like radially like that, then you see those little circles. So when I apply T, depending on where that circle is, it is rotated. So if, for example, if I took it here, then that circle will just remain invariant fixed points. S1 cross 1 would remain fixed point, but otherwise each of the circle is rotated every time. If I apply T, say this one will go there, and then second time apply it will go like that. It will just rotate in each circle. Okay. Now, for example, the first time I apply T, the orbit of any point, not any points, orbit of any point is shifted like this, so it goes round like this. For example, here so this is not really a torus picture because it cannot be angular, but this is just to give you an idea that when I apply T, everywhere it's twisted a little and it goes round the circle with one twist. Then when I apply T square, it has 2 twists and so on. So this is, I believe, maybe 8 twists. So of course it's a twist of a smooth surface, but here I have put this to give you some idea that that is how everything is rotated. So if I do 8 times, it's rotated. T to the power 8 would rotate 8 times. And as I take infinity, as I converge towards infinity, there will be so many twists. But remember, if I cross at any point, those circles are invariant and they just keep twisting every time and many times. So that was my example for compact, and this is always true. For compact space, distality and minimal orbit closures are equivalent property, even if it is not a group. Even in set of integers, you can add 2 integers, right? And inverse is there. So I'm going to talk about just this distality and orbit. So if I have minimal orbit closure, it always implies distality for group actions, because if I take identity, then identity stands alone, right? It is T invariant and it is a closed set, right? So when I have that the whole group is splitting into invariant components, nothing can go to identity, because identity stands alone by itself with T invariance. So nothing can go to identity if I have minimal orbit closures, right? Because if it was identity was in another orbit closure, then that becomes a proper closed invariant subset, closed subset. T invariant subset. So MOC, minimal orbit closures, always imply distality. What about converse? Converse we would like to discuss if this question is true. So does distality implies minimal orbit closure? That would give me a nice representation, nice presentation of the space, nice splitting of the space and components. And one would expect this to be true for many actions. So as for compact space, it was true. So what I'm asking is, if T is distal, as I have defined, that no orbit goes close to our identity, or 2 elements have 2 distinct orbits not converging in infinity to each other, or not converging to diagonal, then does it mean the closure of T and X? And if I took a action of TT, here I have written wrong, is it a minimal closed invariant set? It's a very simple question, and it was known for compact spaces and also for Lie groups and so on, but it was not known for, so only connected Lie groups, of course. And you can also, It's easy to see for discrete spaces because anyway orbits are closed sets. So here it is indeed true that on a locally compact group, distality and emulsy are two equivalent property, and if this is namely if you have T action or TT action, it's distal if and only if it has minimal orbit closure property. And for example, on Lie groups, you can take Lie groups as a group GL and R, or any subgroups of GL, closed subgroups of GL and R are all Lie groups. Okay, so this is group of invertible matrices, and you take linear transformation, and as I mentioned earlier, that the action means that on Lie algebra the eigenvalues are of absolute value 1, and this it was shown earlier, and so to extend from Lie groups to locally compact group, one has to do separately for totally disconnected groups. And then there are other things like when you have a group, if I go modulo a normal subgroup, does distality carry over, and conversely, and does MOC carry over, minimal orbit closure. So suppose G is this group and H is a compact normal subgroup. If T action, which is T invariant, then T action on G, if it's distal, is T action, induced action on G by H, is it distal, and conversely. And same thing for minimal orbit closure. So you have to, so for the proof one uses these kind of arguments, then for totally disconnected space for Lie groups, and then some kind of combination. So a lot of Lie group theory, but apart from that one uses structure theory for locally compact groups. And actually these results are true for action of compactly generated abelian groups, and one can do more things about it, but I think I'll stop here. Thank you very much. I guess my lecture was crystal clear, so nobody has. Oh, yeah, there is.
Pendulum, does it matter that the omegas are rational multiples of each other or irrational?
Yeah, actually it does depend on the relative length of the, I didn't go into detail, but it does depend on the relative length of the double pendulum, how the orbit is. It's not always true, sorry. I didn't want to make it too technical.
Any other question?
Thank you very much.
Welcome you all back. It's my pleasure to introduce my long-term associate and my ex-colleague in IIT Delhi, Professor Rama Mishra. Rama has got her PhD from IIT Bombay, and she spent as postdoc in HRI, that is Harishchandra Research Institute at Allahabad, and later on at Indian Statistical Institute, Delhi. She has taught in two IITs, first in IIT Kharagpur, and later on joined the IIT Delhi. And then she resigned from both the places, and then went as a visiting, she had a visiting position in Japan as a JSPS fellow. In fact, if you remember, even the previous speaker is a JSPS fellow. In fact, anyone who wants to know about that scholarship, please contact these two speakers. They will be able to tell you about that. She was a JSPS fellow in Japan, and she was a visiting faculty at Bose State University at the United States. She is currently a faculty at IISER in Pune, and she works in knot theory and uses real algebraic geometry for her research. Today she will speak on polynomials in knot theory. Professor Rama Mishra.
So I take this opportunity to thank the organizers, Jaya, who is my friend anyway, and Vaijanti Chari. So because of them I am here and I can talk in front of you. So about IISER anyway, Now everyone has heard that I'm teaching in IISER, and IISER Pune is also a new institute. And this talk that I am going to talk is quite elementary. It would serve as an introductory lectures for knot theory, which is relatively a new subject and does not require too much of prerequisite. So many of you, if you hear this, you can start. In fact, there are a lot of open questions and research problems which do not require heavy mathematical tools. So one can really get started and do research in this area. So this polynomials in knot theory, this I deliberately chose because if someone has read little bit of knot theory, must have heard of lot of polynomial invariants. Like Jones polynomial is one of the major breakthroughs in this area, which was discovered in early 90s, and it gave Fields Medal to the person who invented it, and many other invariants are polynomial invariants. And I myself, for my PhD work, have worked on polynomial representations of knots. So there again polynomials I use heavily, and polynomials are functions which everyone is familiar with from school. Sixth standard onwards, everyone knows what a polynomial function is, and for doing calculus, for any other things, it's kind of the most simple function to deal with. So I don't need to really tell about polynomials. What I would start with is what knot theory is about. So let me start. See, knots are found everywhere. You can start your day, if you wear shoes, you tie your shoelaces with knots, and people who are executives, they wear ties and they make knots. And all girls, I don't have long hair, but those who have, they tie their plaits using knots. So in the real life situation, you come across knots. Now, for fun, you can try tying so many different kinds of knots. So it's kind of a pattern thing, like if you take a thing and you every day try making a different knots. So mathematicians are in habit of doing some kind of maths for whenever there is some counting involved. If you want to say how many ways can you tie knots in your shoelaces. So that gave inspiration for mathematicians to develop this theory, this deep subject called knot theory. And what they do is they treat knots as some kind of mathematical objects. Now, this is what I'm saying, that just this inspired mathematicians. It's for fun. The basic root of knot theory started with physicists. So there was a theory proposed that all matters are made of knots. So that was long ago. They proposed a theory which is called vertex theory of ether, where knots were thought of as main objects. And to really classify them and understand them, people who were mathematicians like Tate and all, they were combinatorics people, and they just took it as a simple combinatorial problem that will list all possible knots that can exist in 3 space. So since then it was kind of interesting. Later the physics theory was not, it got disproved. So later on it came up with this what Mendeleev's periodic tables. If this theory was true, then in place of periodic tables we would have had knot tables. So now let me define what a knot is in terms of mathematics, because we want to do mathematics with knots. So in a simple language, knot is a simple closed curve which sits inside 3-dimensional space. So by simple closed curve, you mean you take a thread and you can embed it in various ways. So I'll just show you how you can do it. So you can draw pictures like you can take a thread and suppose you just put it in 3 space. So we are in 3 space. If you just join, you haven't done anything. It's just this is a simple closed loop. So this sort of knot, we call it a unknot or a trivial knot. But then in 3 space, we have freedom for the strand to go under or over. So it might, I can take a thread and make it go first up and then below, and then finally I join it. So it might turn out like you may not be able to now make it like an unknot. So you can do this kind of activity several times. So how many times it goes under or over, we call it a crossing, or we say that these many crossing number is there. Now if we want to actually define it mathematically where we can really work, so I am taking deliberately image of a smooth embedding. So closed loop represents circle, and we want to say we have an embedding of circle in 3-dimensional space, and that embedding I am taking smooth, which is not really necessary to define a knot. One could just take a topological embedding and that is also a knot. But why I am taking smooth? Because I want to ensure that the number of times it goes under or over is finite. And for knot theorists, that makes life much simpler. Because if you don't assume that, you may have infinitely many intersections, and that is what is called wild knot, and that subject becomes really difficult to handle. So for me, my knot is a smooth embedding of circle in 3 space. Now just to make things look symmetric, one can always consider knot as a smooth embedding of S1 in 3 sphere, S3, because R3 is anyway sitting inside S3. So my knot I would now take as embedding of, smooth embedding of S1 in S3. Now suppose I want to classify, I want to enumerate, and I want to study how many knots exist, or in what ways you can consider them to be equivalent. Now each one of them is just an embedding of, image of an embedding of S1 in S3 by a smooth embedding. So they all are diffeomorphic to S1. So this criteria that of a topological diffeomorphism, that doesn't work here, because up to diffeomorphism they all are same as unit circle. So one needs to have some other criteria for classifying them. Okay. So knot theory, this subject, it studies what is called placement problem. By placement problem, we have some other kind of equivalence. We want to know how one space sits inside another space, in how many ways you can do that. Okay. So these are some examples of some interesting classes of knots. So this first class, we call it a torus knots, and now it's easy for me to explain because Riddhi just talked about torus. So all of you know what torus is, S1 cross S1, and torus is embedded in 3 space. So suppose when you are giving your embedding, suppose the image lies on a torus, the entire image is contained on torus. So once it is contained on torus, you know, torus has 2 circles. One is called meridian and another is called longitude. So it's like S1 cross S1, one is this way and one is this way. So when you draw the embedding, it takes some rounds around it might wind some P rounds around meridian and Q rounds around longitude. Then we say it's a torus knot of type P comma Q. Now here it is necessary that P and Q are co-prime. If they are not, then it won't be an embedding. So it's like simple maps. For instance, suppose one wants to write down S1 to S1 cross S1, say take Z going to Z comma P, sorry, Z raised to the power P comma Z raised to the power Q. This map, one can with elementary topology knowledge, one can try proving it to be an embedding. It's a smooth map, all that is fine. But the 1-1 property would happen only when P and Q are coprime. So all these are torus knots of type, say the first one is 2, 3, the one which I actually showed you. It's called trefoil knot. It's a torus knot of type 2, 3. The second one is 3, 7 torus knot. This is 5, 4. So it's quite interesting to see torus knots. Another important class is called 2 bridge knots. 2 bridge knots, again this bridge, I am not defining it because I am focusing more on polynomials and I want to reach to that. So this bridge number is one good property for knots, and that measures if you are trying to draw or you have it in 3 space in the direction of say Z axis, how many maxima it makes the embedding. If you try finding out its number of maxima and minima, the number of maxima is called bridge number, and here by 2 bridge knots we mean if the bridge number is 2. And they are also called rational knots because they have some kind of representation using what do you say, this some number theoretic thing, using some tangles, and so they can be represented by some kind of rational number P upon Q. So they are also called rational knots, and these are all alternating knots. So here what will happen is always this crossings would, this over crossings and under crossing will always alternate. So there are some non-alternating knots, but they are starting with crossing number 8. So up to 7 crossings, all knots are alternating, and in fact most of the knots up to 7 crossings, they all are 2 bridge knots. With 8 crossings, some are 2 bridge and some have higher bridge number. Then these are another interesting classes of knots. They are called twist knots. Now all of them come with, if you take a strand and you keep twisting them, at the end you just bring the loop, go through the other. So just because that loop goes, it becomes knotted. Otherwise the twisting doesn't give any knotting. If you just twist, you can untwist it. Okay. So now whatever I've been talking about, we still need to know when would we say one knot is equivalent to another knot. So in a layman's language, you take a thing, suppose you have a knot and you just play with it, you don't cut it or tear it or destroy it. If you can convert it into a different knot, another knot, then you will say that these two are equivalent. So for instance, suppose I make it like this. See this one, the one I am joining, this is trefoil knot. Whatever I do, I pull or stretch or do, I am not able to really open it. But in case my embedding was, I just switch one over crossing to another crossing, just over to under. Now this looks very much like knot, but see, I am not opening it, I am not doing, but this loop, because of both being over, I can just keep pulling it and I will be able to get an unknot. So this embedding that I just made, it is actually equivalent to an unknot. But there are cases where you may not be able to change it just by playing with it and things like this. So how do you know that they are equivalent or they are not equivalent? See, for instance, these two that I am drawing, if you see carefully, you may think both of them are trefoil. They are both trefoil, true. But watch carefully, one is the mirror image of the other. Okay? So if you reflect by a mirror, you will get another one. Now, if I had two such wires, I could have made this as well as this, and we can start trying. However hard we try, we cannot convert this into another one. So these two are not equivalent. This particular trefoil knot, so one is called right hand trefoil and another is called left hand trefoil, and they are not equivalent. So this property in knot, when a knot is not equivalent to its mirror image, we call it as chiral. So this chirality, it's kind of like, it's a property. It occurs in chemical molecules also. People in chemistry, they study chirality, and this knot has this property that it's chiral. But there are knots which are equivalent to their mirror images. I'll show some example where a knot is actually equivalent to its mirror image. Through playing with it, you can convert a knot to its mirror image. So those knots will be called achiral, or there's another name, amphichiral. So trefoil knot is chiral, but right now we do not know how to prove this. I'm just saying that if I start playing with it, I'll not be able to convert this to another one. Okay? So we require some kind of mathematical proof that this is actually chiral. Okay? So now if I want to define equivalence formally, so there are two knots, suppose K1 and K2. K1 is defined by embedding phi1. So K1 is image of phi1, which is embedding of S1 to S3. K2 is embedding of phi2 from S1 to S3. And we say that these two are equivalent if we have an orientation preserving diffeomorphism. Now this term, if you have not heard, if you have done differential topology, you must have learned what a diffeomorphism means. Yes? You have a question? Okay. So diffeomorphism from S3 to S3, and we want it to be orientation preserving, precisely because to take care of a knot and its mirror image. If we don't put, then every knot would be equivalent to its mirror image, which is not really the case. So we require orientation preserving diffeomorphism, which if you compose phi1 with this, you get phi2. So which is same thing as saying, if you imagine there is something happening, the transformation is happening at the level of S3, the ambient space, and through the transformation one image gets converted into another image. So if that can happen, then we say that one knot is equivalent to another knot. Now this, whatever formal definition is, it matches with the idea of intuitive equivalence. Now you cannot really prove a knot to be equivalent to another knot or not equivalent to another knot using this definition. Each time it's not possible to produce a diffeomorphism. So we require some tools to at least be able to say that this knot is not equivalent to another knot. This much itself would help in classifying. Okay? So what knot theorists do, they try finding out, they try associating some values, either they are numbers or they are some structures like group or ring, or many of them are polynomials. So these things that we attach to this, to a knot, we call them knot invariants, because we prove that if two knots are equivalent, the associated things are same. Whether if it's a number, for equivalent knots, they should be same, equal numbers. If it's a group, then for equivalent knots, the groups should be isomorphic. If it's polynomial, for equivalent knots, it should be the same polynomial. Okay? So they are called knot invariants. Now knot theory, the entire knot theory is talking about finding more and more powerful invariants, because none of them have really served the 100% purpose. So the first thing in the beginning, when one wanted to classify knots, for topologists the thing that comes to mind is why not take the complement, because the knot is embedded in, it's a subspace, it's one-dimensional submanifold of S3. So just take the complement, which is a topological space, and from the definition of ambient isotopy, it is clear that if phi1 and phi2 are isotopic, then the complements would be diffeomorphic. So this would serve as an invariant, and surprisingly, it's actually a complete invariant. The theorem for knots has been proved that if two knots are equivalent, if and only if their complements are diffeomorphic. But then this particular invariant doesn't serve much purpose as far as practical thing is concerned, because you get two different three manifolds. It's not easy to prove that they're diffeomorphic or they're not diffeomorphic. That itself is an open problem, still not completely solved. So next what we do, once we have the space S3 minus K, we can do algebraic topology. We take fundamental group. You must have heard about fundamental group of a space. So S3 minus K is path connected, so we can talk about its fundamental group. And we can prove that if K1 is equivalent to K2, then these groups, pi1 of S3 minus K1, will be isomorphic to pi1 of S3 minus K2. So fine, it's a nice invariant. It helps in proving when a knot is not a trivial knot. That it has successfully detected. So we have a theorem that a knot is an unknot if and only if its knot group is infinite cyclic. So if the knot group you compute, and computing knot group is very combinatorial. I haven't written it in my slide. So it's not difficult once you draw what is called knot diagram. I'll be talking about it shortly. From the knot diagram, it's very simple to really write down a nice, you can write down the generators and the relations. So you can describe this group combinatorially just from the diagram. So you can find the group, and the moment you see this group is not infinite cyclic, then you can say it's actually a knot. It's not a trivial knot. But then this invariant is weak in the sense any knot and its mirror image will always have isomorphic groups. This pi1 of S3 minus K and pi1 of S3 minus K mirror image will always be isomorphic. So this can never detect chirality. So this was something which was kind of, we didn't like, knot theorists didn't like it, that this invariant is very weak. It can't even detect a knot from its mirror image. So now to find more and more invariants, we need to have some simple situation where we can compute more, we can define more invariants. And if you look at knots as embedding into 3 space, the way I am showing you in the air, you can't really do much with that. So to make life simpler, we would want to project it into a nice plane, and then we want to capture all the information so that it describes that particular knot. So what we do is, we have to choose a nice image, a nice plane, so that you get a good projection. Now if I just project it into any plane, because it has undercrossings and overcrossing, so suppose the embedding was having one crossing and then top of another crossing and then another crossing, and it is embedding in 3 space, and suppose I choose a plane perpendicular to this direction, then all of them will collapse to the same point, and then I will not have any information how to really represent this knot, only from the projected image. So we want to avoid this kind of situation. And we know that you take any direction, there is a plane perpendicular to it. So you have to carefully choose the plane. So now here the assumption that I am dealing with smooth embedding is useful, because first of all I know there are only finitely many times my curve has crossed. The self intersections are finite. So now whichever plane the direction is going to give me something wrong, they are only finite. There will be only finitely many directions. If I choose a plane perpendicular to that, will give me things which are like shown in B, C and D. So we don't want projection to have a cusp. We don't want projection to have a multiple point. We don't want projection to have a tangential intersection as shown in C. But looking at the embedding, there are since finitely many crossings and there are only finitely many directions which could make things bad. So we can just avoid them. And since we have so many directions, I can just take the complement of that. So any direction which is different from these finitely many, if I choose a plane perpendicular to that, would give me a projection which we call, which would be a generic immersion, where by generic immersion we mean that in the projected image you just have this double points which are transverse. Transverse double point meaning you have a different tangent at each. So this kind of, I justified that this kind of projection always exists because we are in the smooth category. And in fact, from algebraic geometry argument, this set of such projections is actually an open and dense set in the space of all projections. And we call this projection as a regular projection. So a typical regular projection of trefoil knot would look like this. So now when you project, you have double points. Now the crossings are actually, the map is not 1-1, it's touching. So you don't know which strand is above which strand in the knot. The information is lost. Like when I made trefoil, and if I switch one crossing, as far as projection is concerned, both will give me the same projection. So from the projection you cannot make out which embedding it has been. So to capture the information of knot and to actually describe knot, you need to provide information at each double point. You want to represent which was over strand and which was under strand, and you can do it diagrammatically on paper by just providing this sort of, like you make a cut and show that clearly that this was an over crossing and this is an under crossing. So now what you get is called a knot diagram. Now these knot diagrams have served a fantastic purpose in terms of computing knot invariants, and diagrams are the combinatorial objects where you can find connection of this with even physics, because each diagram, again this I have not written it, but just for the information, that each diagram you can generate by 3 or 4 simple objects. Like you require an overcrossing, you require an undercrossing, and you require a minima and a maxima, which we call cup and cap. So if you have 4 objects, any diagram you can write as product of these 4 things, and there is a complete diagrammatics that everything you can write down in terms of diagrams. So the diagrams are sufficient data to tell you about knots, except because there are too many diagrams possible for the same embedding, because the projections, the directions where you can find plane perpendicular to it, They are infinite. So maybe you can project it in two different planes and get two different diagrams. Now both diagrams are nice, they are all regular projections. They may look different, but they actually represent same embedding. So they represent same knot. So how to ensure that looking at the diagram, it may not look that they represent the same knot. So we need some kind of equivalence at the diagram level, which is powerful enough to detect that you can actually, if the knots are equivalent, then you should be able to convert one diagram into the another diagram and vice versa. So we have at the diagram level certain moves which are known as Rydemeister's moves, and they are like the three types, and they're easy to explain because you can practically do it. You take a strand, if you make a twist, suppose the first one just says that you have a twist like this, and suppose I had a embedding like this which was making one twist, but it's still a embedding of circle, and I can actually untwist it and make it an unknot. So a twist can always be straightened. And the second one is again very topological, that you can just pull them apart because a strand is completely going below twice consecutive undercrossings. So all you need is just to pull and make them separate. The third one is a bit not so intuitive, but you can take rods, and suppose you have three rods that you can just think of them as like locally at one place. You have one rod crossing like this, and a third rod is completely below both of them. So you can slowly slide it up and make it convert it into this, and each one of them is reversible. So the equivalent. So these three moves, they define equivalence at diagram level, and we have this theorem that two diagrams represent isotopic knots if and only if one can be transformed into the other by a sequence of finitely many Rydemeister's move. Okay. Yes? No, see, regular projections would be many, it's an open and dense set. That's why there are many knot invariants which are defined at the level of diagram, and they say, for instance, the bridge number of the knot. We define it at the level of diagram, and then we say that is called bridge number of that diagram, and bridge number of the knot is minimum of bridge numbers taken over all possible projections. And that's why it is difficult to compute. No, we cannot say that. We cannot say that. Finitely many projections are bad, but the regular projections are open and dense. The crossings are finitely many, but then you have so many choice. No, it won't be finitely many because many of them may give you the similar thing. But the number of projections are actually, the regular projections are infinite, they are open and dense. So through, yeah?
What if you go modulo, say some kind of an equivalence in that projections, so that if two projections are same looking, you call them equivalent?
That's what we are doing. That's what we are, this Rydemeister's move is precisely that, because you may have two different projections that they will give you two different diagrams, but equivalence is through these moves. You will be able to convert one into the other with the help of these moves.
No, what I mean is that not even at the level of these moves, but just if you look at an immersion of a circle in a plane, you have immersions which can be isotopic. So
exactly. So those natural topological move you can anyway use. they are all naturally topologically same. So for instance, like my embedding may, for instance, at the level of the circle, it may be just like this, or it may be smaller, or it may do some polygonal kind of thing, but they all are topologically same. These moves deal with when you actually have crossings, and you may get lot of extra crossing, and it may look like you can draw a knot diagram of an unknot in a very complicated way, which on the surface may not look like an unknot. But if you use these Rydemeister's move carefully, you will be able to convert, simplify that diagram to something which does not have any crossing. So that particular complicated diagram is basically a projection. Some particular plane gave you so many extra crossing because in the 3 space the embedding was zigzag like this, and you chose a plane so that it gave you a lot of double points. But actually those double points are not there. You get the point? So this is where I demonstrate. So you start with this picture in the beginning. It's called figure 8 knot. It has 4 crossings, and using Rydemeister's move cleverly a couple of times, one can show at the end that you get back the mirror image of that. See, the last one is mirror image of the first one. So figure 8 knot is actually amphichiral, and these 2 knot diagrams can be shown to be equivalent using only Rydemeister's move. To actually practice Rydemeister move, you require a bit of concentration. So if you want to do it and check each step how it's been used, we can do this exercise after the lecture. So I have the slide, or I can draw it and show, or you can do it with this wire, because you can actually practically do it, what is being done here. Each step you can take this wire and perform and do it. Okay?
Sorry.
So,
Do you have computer programs which do Rydemeister moves?
computer programs for Rydemeister, yeah, even how many Rydemeister's move are required, some people are doing this kind of thing, but yeah, for knot theory now many of the stuff has been there on the website. There is a person called Barnaton who has made a knot atlas, and many of the invariants has been, actually he has developed program which can be computed. So now there are many structures which we can associate, like we want to have knot invariants. So you take a knot diagram, they all are defined at the level of diagram. So you take a diagram and write down something, or find something. For instance, this you define something, and then you say that if you can check that particular quantity, for instance a polynomial, if we define using diagram, all we need is to check that it remains invariant under all 3 moves. If you can prove that, because you are using diagram to define something, all you need is to check the invariance under all 3 moves, and then if it is satisfying that it is invariant, then it would be served as a knot invariant. So you can make a lot of knot invariants, and many of the knot invariants are polynomials. I would give a small reason which I just found on the web, and I felt convinced that why, because even I used to wonder why lot of knot invariants are polynomials. Starts with Alexander polynomial, and then Conway polynomial, then Jones polynomial, Homefly polynomial. Why people thought about bringing polynomials as knot invariants, and each one of them was actually defined using some other connection, either using some kind of matrix or some braid group representation. Now this knot theory is actually connected in various ways to other branches in pure mathematics. You can come across knot theory, you can learn through group theory, like you can take braids, which I am not mentioning. So braids and knots are also connected, and you can obtain many knot invariants using braid groups. So the reason why many knot invariants are often polynomials, so I'll just give a quick thing. First we need to, I said in the beginning that knots can be treated as mathematical objects. So suppose we have two knots and we want to have some kind of operation between knots so that we get another knot. So this is one simple operation that is done with knots, on knots, like you take two knots, you choose some smooth arc away from all the crossings and remove the interior of it in both of them and just glue them along the boundary, the points. So as in topology people do connected sum in any other manifolds. So the similar, it's a one-dimensional manifold, so we are removing interior of a one-dimensional disk and gluing them along the boundary. So what we get, we call that as a connected sum of K1 and K2. Now if you have a knot which is connected sum of two non-trivial knots, it's easy to see that if you connect it with a trivial knot, you take a knot, another one is a trivial knot, you don't get anything new, you get the same knot with the connected sum. So every knot is connected sum of itself and a trivial knot. So in case both of them are non-trivial knots, then those knots we call as composite knots, and those knots which are not connected sum, you can't find another non-trivial knot to connect it, we call them prime knots. So knots also have this prime decomposition kind of thing as we have for integers. Now with respect to this connected sum operation, if we take suppose equivalence classes of knots, now we don't deal with individual knots up to ambient isotopy, suppose we consider them same, take equivalence classes of knots and use this connected sum operation, you can see that this set will form a commutative monoid. It has an identity element, it's commutative, but you cannot have inverse, so it's not really a group. It may not be even a semi-group, but it's a monoid. Now if you take, the moment you have a monoid structure, you take formal linear combination over the coefficient you can take from any field or ring or anything. So take a formal linear combination of elements of G, and you can formally, now when it's formal linear combination, you can add two elements because you can use plus operation of that particular coefficient ring, and the product you can use this connected sum operation. So with respect to these two operations, we can see that this which I am denoting by Kg, it has a ring structure, and in fact it's a free ring with prime knots as generators. Now with knots we could make a free ring structure, and polynomial rings are canonically free rings. So in some sense we can say that knots can be treated as polynomials. So once you have this ring of knots and you have some polynomial ring, we can try giving some kind of representations, and that's why it has become easy to give more polynomial invariants. Now all these polynomial invariants that exist thus far, they all have roots coming from higher mathematics. For instance, Jones polynomial comes from operator algebras, but each one of them have some kind of algorithm, very combinatorial, which one can use as far as computations is concerned, and it's been checked that they are all not invariants. One can define them only at diagram level. Take a knot diagram and just use those algorithm, and since it's been checked that they will remain invariant under Reidemeister's move, so it doesn't matter which diagram you take. You take a knot, take a suitable diagram that suits you and use these algorithms, and you will be able to compute this polynomial invariance. So I'll describe few of them. So before I actually give these polynomial those invariants, we need to define a few terms like orientation. It's easy to define. Orientation is just giving directions. So one can give two possible orientations to any knot, and we say this knot is with the opposite orientation with the other. So another property of knot is, suppose same knot you give one orientation and you give another orientation. Sometimes they may not be equivalent. There are knots which are not equivalent to if you change the orientation. So those knots which are equivalent by changing the orientation, we call them invertible knots. So again, invertibility is a property which is invariant. Okay. So another thing, once we have oriented knot, then at each crossing we can assign a sign, plus 1 or minus 1 in the following way. So the rule is, if the overcrossing moves anti-clockwise to meet the undercrossing strand, then that is considered positive. So the second one is plus 1, because you see the over strand, if you want to join it with the under strand, then you have to move anti-clockwise. The other one is clockwise, so it is minus 1. So when you have orientation, you have concept of sign, and in any knot diagram, suppose it's an oriented knot diagram, you give plus 1 or minus 1 at each crossing, and if you add them up, what you get is called right. So right is just the sum of all the signs. Second notion that is useful in describing those polynomial invariants is Skein relation. Now Skein relation is also described at the level, it's a local thing. At one particular, suppose you have 3 diagrams which are identical everywhere except at one crossing. Rest of the places all pattern is same, only at one crossing the first one has a positive crossing. See, if you want to move it to the under one, you have to move anti-clockwise, so it's plus, so we call it K plus. The second one is K minus, and the third one is where matching the orientation you just split, you avoid the crossing and you say you have smoothened it. So K plus, K minus, K naught, these 3 are said to be in Skein relation. They are Skein related diagrams. Okay. Next notion is of smoothing. It's not coming in this, I think. This slide is got something wrong. But by smoothing we mean, I can just describe, or maybe I can draw what smoothing would mean. It's from the first one itself. Suppose instead of, this is also one I said it is smoothing. You could do another smoothing by simply joining other 2 regions. See, if you have a crossing, you have 4 regions. So either you could join, when you did smoothen like this, you join the upper region with the lower region. Now if you smooth the other way around, you make a U. You make a cup and a cap. So you are joining the right region with the left region. Okay. So that is another kind of smoothing. So now we are in a position to describe these polynomial invariants combinatorially, because I just wanted to show how to compute these invariants. So the first one, this Alexander polynomial, was the first not invariant polynomial invariant. It was discovered in 1928, and until 1980s this was the only polynomial invariant, and it was defined using concept like determinant of a matrix, but now we can compute it using these algorithms. So the first one says, give the value, this polynomial for unknot is always 1. So if there is no crossing, you get a plain circle, you say that this is 1. And suppose you have 2 unknots. Now here you may wonder, if we are in knots, why do we have 2 unknots? So knots have been generalized to links. Links, I didn't want to bring it, but there is a need. So instead of one circle, suppose you are studying many circles. There are some finitely many circles and you are considering this joint union of them and you are embedding them in, say, three-dimensional sphere. So individually each circle would form a knot there, might go under and over, but between circles also they may get linked. It might happen that one circle individually both of them are unknot, but they might get linked like this. So you may have linking between knots. Okay? So as a manifold we can say one-dimensional manifolds, you may have like several components to it. Okay? So here suppose you have two unknots, that means two circles have been just unknot and they are not even linked, that disjoint union. So they are unlinked with two unknots. Okay? So this polynomial gives value 0 to that. And the third one which actually helps in computation is this, which is kind of recursive. So if you have three diagrams which are scheme related, then this linear relation is satisfied. So the value, ultimately the polynomial that you get, these are not really polynomials, they are Lorentz polynomials in some ring where there are negative powers also. So depending upon what field you are, suppose you are with field of real numbers, you can have a polynomial having variable. So if you use these three rules, you write down any diagram, you will be able to compute the polynomial of that diagram, precisely because this, when you switch a crossing, you start with one crossing. For instance, you have a trefoil, you concentrate on one crossing, you call that, suppose that crossing is plus. Now you have to have orientation, you have to see whether it's a plus or a minus. Depending upon the orientation, any crossing would be either plus or minus. So keep that as it is. If it is plus, then you make another diagram by switching the crossing, that would be minus. And third diagram with smoothing them. Now you will see that each time when you switch or you smooth, those two pictures would get simplified. Now third time again you do, this is the one that you want to compute, keep it as it is, but the simplified diagram, now you take another crossing, you do the same. So if you keep making these iterations, at the end you will see that you will get some finitely many unknots. And for unknots you know the value. So with third relation you will be able to compute the Lorentz polynomial, whatever this Alexander polynomial, its value. So these algorithm, these three rules are very algorithmic that you can actually compute and get the value. Yeah? Pardon? It's already 12 o'clock. Shit, I haven't yet. So I'll take, okay, conclude it in, I thought I prepared less, but I don't know how. So we have another bracket polynomial. It's very effective. So I won't be now explaining. So then we have Kaufman polynomial. This bracket polynomial is something where you don't really get an invariant because the right plays a role. So one multiplies by some factor and gets some polynomial which is an invariant. Now Jones polynomial, which is kind of celebrity, this is just change of variable. For Kaufman polynomial and Jones polynomial are same, and there are few generalization like Homefly polynomial. They give you two variable polynomials. So this is about polynomial invariants. I had another section for parametrization, so that I wouldn't really spend time, maybe maximum 5 minutes. So this is what I work on. What I described thus far was an introductory thing for knot theory. And here, if you look at now, instead of taking a compact knot, suppose you just open the ends and let the ends go to infinity. You get something which is called open knot, and that here from S3 also you can now remove the corresponding point and be in R3. So you can have embeddings of R in R3. Now R in R3, any smooth embedding would be given by 3 smooth functions. And those smooth functions could be polynomials, because polynomials are the best possible smooth functions. And up to isotopy, one can prove that all knots can be represented by polynomial embeddings. So up to equivalence, you don't have to worry about other smooth functions. You can really find polynomial embeddings which would give you that particular knot. And in the polynomial category, you can actually find the equivalence also through polynomials. So we call it polynomial isotopy and so on. Now the research in this field is actually finding out the degrees of the polynomials. You take a concrete knot and write down with least possible degree can you find polynomial representation. You call it a minimal degree sequence and things like this. So what I have done is, for certain classes of knots, found the degree estimates, and some of them I was able to show that they are minimal. So I won't be describing those things, but these are some pictures where concrete knot polynomials has been, the embedding has been written. So it's an open trefoil knot. If you join the ends, you would get the trefoil that you saw. This is figure 8. And the polynomials, if you are interested, I can give you the complete file where these exact polynomials, you can see how, which degrees and so on. So this is again a 5 crossing knots, 6, 7, 8. With 8 crossings, there are 23 knots. But I've just shown a sample that one could write down polynomials, not very big degree. The highest degree is 11 in this, and you find a polynomial embedding. So thank you, I'll stop here. Sorry if I extended the time.
Thanks, Rama, for a very nice lecture. But I don't think we have time for any question. You can ask her question during the lunchtime. So I'll ask for the next speaker.